In my last video about electricity, the thumbnail asked the question, does electricity travel at the speed of light? And I got a lot of comments that said, no, of course not, because electrons have mass and wires have resistance. So electricity can't travel at the speed of light. Now, the conclusion that I arrive at in that video is that electricity does travel at the speed of light, or it's at least so close to the speed of light that for all intents and purposes you can just use c to calculate it. But based on all those questions about resistance of wire, today I'm going to test that. So, in my effort to be like the strangest neighbor possible, I have spent the last few days, well, I set it up the first time like 6 months ago, but I have set up a huge loop of wire in my front yard and the same electronic setup that I used in my last video to time how long it takes electricity to go around this loop. But I don't just have one loop of wire, I have 3 loops of wire with different resistances, different thicknesses of wire. We're going to see if there's a difference. This is almost the same setup that I used in the previous video. The obvious difference being that there's only one loop of wire. In the previous video, I had a loop going out from the battery and switch in both directions, and then approaching the resistor or the light bulb that was the load. And one of those loops really didn't matter, so I've removed it. The other really big change, I guess really small change, I don't know, is that the loop isn't 500 meters anymore. It's only 12 meters because it needs to fit in my front yard. The whole timing setup and how it looks on the oscilloscope should be exactly the same. The way this is wired, I actually didn't have to make it exactly the same. I could have used a simpler setup. But for the sake of comparison, it's identical. And we can still see the delays very clearly on the oscilloscope. So let me show you how that works. So the big loop of wire that extends all the way out there through the front yard comes back to this circuit. So I have this electronic switch here, and when this switch is open, as in before we have flipped the switch and started to flow current through the loop, it's basically holding the entire loop at about 1 volt potential. Now, the actual amount of charge in a wire is, in my mind, the best analog for voltage that you can come up with. It's not perfect because it changes with the local capacitance of the wires and stuff like that, but basically, when this circuit applies a volt to the whole wire, it's depleting that wire of electrons. I actually made an attempt to measure how many electrons I was removing from the wire and got an answer somewhere in the realm of 200 or 300 million electrons. Now that sounds like a lot of electrons, it's a lot of particles, but if you look at the number of free electrons that are in the wire, that's actually less than a quadrillionth of the free electrons in the wire. So it doesn't really seem like very much, but it actually is, and I'll talk more about that later. When this switch closes, it launches a whole bunch of electrons all at once into this alligator clip, which then start that wave propagation thing, and when that wave goes all the way around the loop and comes back, then current starts flowing through this resistor, and we can measure that on the scope. If you saw the last video, this graph is not going to surprise you. The x-axis here is time, and the y-axis is voltage, and we're looking at a variety of signals within the circuit. The yellow trace is the switch. So when this trace goes from low to high, that is when we've actually flipped the switch, and we've launched our pulse of electricity into the circuit. The white trace is the voltage at the other end of the loop. So this is the signal that has gone all the way through the loop and come back that we have to wait for. And if you actually go look and see how far this is, we can measure in time. That's, let's get it right there. Yeah, that's almost 100 nanoseconds. That's 98 nanoseconds. So it takes electricity 98 nanoseconds to go through that loop. When we send this pulse into the loop, 98 nanoseconds, we get this pulse back out the other end. So I know that the loop of wire out there is exactly 28 meters long, because I measured it earlier. But before you actually get to the scope probes where the measurement is made, there's an alligator clip on both sides. So that will add 40 centimeters on each end. So if I take 28.8 meters and divide it by 98 nanoseconds, we get 2.939 meters per second. That is almost C. 98% the speed of light. So in the last video, I guess I didn't know exactly how long the wire was, so I couldn't make this calculation. But here, I can say that the speed of electricity is 98% of C in this configuration that I've got right now, using the 2.4 ohm magnet wire. Now I also have a thinner magnet wire with a total resistance of 6.3 ohms across the entire loop. And that wire has the exact same enamel coating on it as the wire that I just tested. So it should have the same dielectric properties, and we should get the exact same speed, despite the fact that it's a significantly different resistance. So with the new wire hooked up, that cursor is still right on the money. We have not changed the propagation speed one bit. 98 nanoseconds. It is fun when physics works. Cool. But wait, there's more. I also have thicker wire. So it's some of this stuff soldered together into a big 28 meter loop. And this is actually multi-stranded wire. And because it's so much larger, across the entire loop, it only has a resistance of 0.9 ohms. So it's a much lower resistance case. I would expect that as bare wire, this would propagate the electric signal at exactly the same speed as the magnet wire that I just tested. The only thing that could throw a wrench in that is that this is not enameled wire. It's got this thick, like, rubber insulation on the outside, which is going to have a slightly different dielectric effect and could end up slowing the signal down just a tiny little bit. We'll see. I'm very curious. I also want to point out that although it shouldn't matter one bit, I am actually only hanging one of these wires at a time. I'm suspending it off the ground in order to keep it away from the wires that I'm not using. I just have the other ones laying out here, a solid half a meter away, so they should have no impact on the experiment. But I knew that if I didn't say that, people would ask. As I'm tripping through one of the smaller wires, thick wire is all hooked up. Moment of truth, is it still going through the loop at the same speed? Maybe. I might call that a little bit longer. Maybe 99 nanoseconds, or maybe 100 nanoseconds. It didn't change very much, but for the sake of argument here, I'll call this 100. 96% the speed of light. 3 wires, 3 different resistances, the exact same propagation speed, really within measurement error on all of them. And all of them are just about the speed of light in a vacuum, which is just about the speed of light in air, which just so happens to be the thing that's surrounding these wires. So if the resistance of the wire doesn't change the speed at which electricity moves through that wire, what does? To answer that question, we really need to understand how electrons push on each other through a wire. As a quick refresher, let's think about what's happening in this wire at the subatomic scale when the switch is flipped. The electron density in the wire is a little bit below average. Earlier I mentioned that we only actually removed a half of the quadrillionth of the electrons that are able to move in the wire, but for the sake of clarity in this diagram, I've removed a quarter of the electrons. When we flip the switch, all of a sudden we dump a bunch of electrons into one end of the wire. These electrons want to spread out and make the whole wire neutral again, but they don't spread out like this, they spread out like this, where each electron just moves a tiny bit until they're all evenly spaced again. Now in actuality, if you want a steady state current to flow in the wire, you can't actually let the wire reach equilibrium. The electrons want to spread out and make the whole wire neutral, but if the battery keeps pumping electrons into one end of the wire, then they never have time to fully spread out. This means that in steady state, electrons are actually slightly denser right in front of the negative end of the battery, and slightly less dense right in front of the positive end of the battery. Because electrons are charged particles, every single electron emanates from it an electric field. This is something that is inherent to the particle. Like, you can't have an electron and not have it make an electric field. Other charged particles are acted upon by this field. However, the moment we flip the switch and dump all these extra electrons into the end of the wire, the next electrons in the wire don't start moving right away. They need to sense the field of the electrons inside the switch, and this field doesn't travel instantly. It travels at the speed of light. Once this electron scoots forward a bit, it's now emitting its own field from a slightly different place. But the next electron, again, doesn't know that yet, and has to wait for the field to update at the speed of light before it scoots forward, updates its field, and so on. The signal we just measured, the speed of electricity, is not the speed that an electron moves through the wire. It's the time that it takes for an electric field to reach an electron, and for that electron to respond by twitching imperceptibly forward in the wire so that it can in turn apply a tiny force to the next. And this wave of motion happens very quickly. So if you want to slow down electricity, you want to slow down the propagation, the rate at which electrons can shove each other through a wire, you have to limit the electrons' ability to interact. The fields that they use to talk to each other, you've got to find a way to slow that down. And because most of that field is moving outside of the metal wire, you've got to actually change the speed at which fields propagate outside of the conductor. Now, Maxwell has something to say about this. The actual equation that defines the classical speed of light depends on two variables that describe how whatever substance that light is passing through responds to both electric and magnetic fields, which means that if we surround the wire with a material that strongly interacts with electric fields, we should be able to slow down light, and therefore electricity. So, I am about to try to change the speed of electricity. I'm not 100% sure that it's going to work. I'm hoping that this big pipe, once I fill it with water, is actually going to slow down the propagation of electricity in the wire that's running through the middle of that pipe. I think this is going to work because water is a very strong dielectric. Now, dielectrics are substances which are insulating, meaning that they can't have electric currents passed through them. You're not going to get electrons to flow all the way through like a brick of plastic. But dielectrics are polarizable, meaning that they can actually generate a small electric field. Specifically, when you put a dielectric in an electric field, that dielectric material will create its own opposite electric field that partially cancels out the original electric field. And this decrease in intensity of the field comes along with a decrease in propagation speed. Which means that the signal that has to go through that loop should take longer to go through that loop after I fill that tube with water. What am I looking at? Yes, it moved it. A tiny little bit. Check that out. It worked. Okay, so we went from 45.6 nanoseconds to about 50.6. Calculating the slowdown here is surprisingly non-trivial because only a portion of the signal should be slower, plus my initial timing without the water already showed a slightly slower result than the bare wire, but I didn't know that yet because I actually filmed this experiment first, but whatever. Okay, so I just rechecked my math, and the actual slowdown of the electricity passing through that pipe was between 1.4 and 1.5x. That means that the speed of electricity flowing through that pipe was approximately 2/3 the speed of light in a vacuum. We would expect that the speed of propagation of an electric field through a large body of water would be about 9 times slower than the speed of propagation of an electric field in air or vacuum. But that's not what we saw. When I ran electricity through that pipe full of water, it actually only slowed down the propagation of electricity through that wire by about 1.45 times. That's not 9. all matter is going to interact with an electric field just because it has an electron cloud around a nucleus. If you had a water molecule and you all of a sudden applied an electric field to that molecule, the electron clouds around each nucleus would sort of shift just the teeniest little bit in order to cancel out part of that electric field. This has the effect of decreasing the amplitude of the electric field and slowing down the propagation of the electric field. If you let that water molecule sit in the electric field and cook for a while, it will eventually orient itself, like literally rotate the entire molecule to align with the electric field. So now let me come at this from the other end of the spectrum, quite literally. The index of refraction of water is about 1.33. That is the expected slowdown of light, like optical frequency radiation, passing through water. So if we just predicted that water was going to slow down the propagation of electric field by 9x, but light, which is just an oscillating electric field, is only slowed down by 1.33x, what gives? Turns out that the slowdown that you expect is frequency dependent. So if you have that water molecule and you apply an electric field, that sort of slight rearrangement of the electron cloud, that happens like instantly, almost instantly, because the distances are so tiny and the amount of stuff that has to move is so tiny, that just happens. Next, the whole molecule starts to rotate, but that happens really, really slowly. Now, once that molecule rotates, it has a really significant impact on the field. Because of this, we can say that very, very high frequency electric fields, like light that you can see, is going to interact with water molecules very weakly. And very slow electric fields that are going to stay at one polarity for a really long time before flipping and gives the water molecule time to react and time to cancel that field, those frequencies of electric fields are actually going to interact with water more strongly. So the cool thing here is that we have shown that flipping a switch is actually closer in frequency space to light than it is to just having a steady state DC field, which is weird because we're just flipping a switch, it's DC. That's what's happening right here. This is the signal that this is literally the signal being fed into that wire right now. And you can see that we're just, at 1 voltage and then it changes to a different voltage. Also, I want to point out that this equation I gave earlier for the speed of light in terms of the material's permeability and permittivity is very specific. It's the equation for the phase velocity of electromagnetic waves, derived as these perfect, smooth, planar sine waves. And this does not look like this. And the discrepancy here is very important. Imagine that this slope right here was actually part of a sine wave. I want to say, because that's literally what it is, it's literally part of a sine wave, but it feels sort of disingenuous, but sort of not, because the physics works with sine waves. So you can take any signal and decompose it into sine waves. It's called a Fourier transform, and there are oodles of fantastic videos about Fourier transforms and how to take an FFT computationally in order to see all the frequency components that make up a signal. I'm not going to get into that in detail right now, but I'll direct you. I'll link a 3 blue 1 brown video. I'm sure that there's a great 3 blue 1 brown video about FFTs. I've probably watched it. But for right now, imagine that this signal right here is actually made of a whole bunch of sine waves added together. So the way that I have this scope configured right now, it can actually show us all the frequencies that are making up this step. The trick is that I have to show it a bunch of steps. We have to flip that switch on and off and on and off and on and off a whole bunch of times in order to give the scope enough data to properly decompose this step into a whole bunch of sine waves. So I'm just going to zoom out, and you can see that we're turning it on and off and on and off all the time. These are our frequency components. This is an FFT, which means that on the x-axis you have frequency. Think of every point along the x-axis is a sine wave, a signal that could exist in this wire. with a slightly different frequency. And anywhere that this graph peaks, that means that that frequency is basically present. That if you take a sine wave of this frequency, and 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 all of these peaks, and you add them all together, that you'll get that shape. That you'll get this switch on characteristic where we're flat and then we ramp really quick and then we're flat. All of the equations that we use in physics to govern the propagation of fields are much simpler and rely on the fact that these fields are going to be like sinusoidally varying, that you have some sort of regular oscillating signal. It just makes the math work. So a signal like this could be construed as the sum of a lot of independent signals that all by themselves are propagating through that wire. And only when you add all of those signals together does it actually give you the shape and give you the reality of the situation, that we're just flipping a switch. When we're assuming that the field passing through the water is, a nice sinusoidal, continuously varying thing, why can't we say that the water in that pipe is reacting to all of the individual frequencies that actually make up this signal? That's the kicker. So in the last video, I had a lot of questions that were talking about AC versus DC. Like, okay, so you're flipping a switch on and you're using direct current to, push a signal down the wire, and then the signal comes back down the other wire. The answer is that it's all AC. The act of flipping a switch actually has frequency components. All of these frequencies of signals are occurring at the same time and adding together. But look at how many different frequencies we need in order to actually see this switch on characteristic. The act of flipping a switch is AC. Like, you are changing an electric field. You're changing the current flowing through the wire. These are really fast frequencies. That electric field that is associated with like one of these spike sine waves is going really fast, which is why it seems like we're closer to light than we are to a static electric field, which is just so cool. So after all of these tests, we see that the speed of electricity has less to do with the wire and more to do with the speed at which electrons communicate with each other. And since this happens at the speed of light, in order to change the speed of electricity, we have to locally change the speed of light by filling space with some material that interacts strongly with electromagnetic fields, because the speed of light in that material is going to be different than speed of light in something like air or vacuum. The really freaky thing is that light of different frequencies travels at different speeds in different media. And the question that always really kicks around in my mind is whether or not reality is actually made of all of these simultaneously occurring waves that, coalesce into something that looks like it makes sense to us, or whether this set of waves everywhere is just how our very human mathematics makes sense of the world. I really like the Westworld line, if you can't tell the difference, does it really matter? But in this case, I think that a physicist might say, if it produces the same observable, it's an equally valid wave function. That's way too corny of a line to end on. So I guess in this video, I talked about how resistance doesn't actually affect the speed of electricity. But in the next video, I'm going to talk about what resistance does affect, and that's the speed of electrons. So I'll see you then.